Hello students and welcome to the third lecture of Unit 2. Here we will discuss the Gibbs Duhem equation and try to derive it. So the Gibbs Duhem equation is named after two scientists, Josiah Willard Gibbs and Pierre Duhem. This equation in thermodynamics describes the relationship between changes in chemical potential for components in a thermodynamic system. And it states that the intensive properties are not independent but are actually related. The Gibbs Duhem equation cannot be used for small thermodynamic systems because of the influence of surface effects and other microscopic phenomena. But it helps us to calculate the relationship between quantities as a system which remains in equilibrium. What is the Gibbs Duhem equation? For a system at equilibrium, the Gibbs Duhem equation must hold and is given by summation of product of number of moles for each component Ni into, that is the product of Ni into d mu I, where d mu I is the change in chemical potential for each component, where I defines the component, must be equal to 0. So this relationship, what it does, it places a compositional constraint. What is a compositional constraint? That is, what is the composition of the mixture. So a compositional constraint upon changes in chemical potential in a mixture. What is the condition? The condition is at constant temperature and pressure for a particular composition. So this result can be derived by considering mu I, which represents the partial molar Gibbs function for a component. So what is the derivation? We already know Gibbs free energy G is a function of pressure, temperature, and suppose there are 4 components in the mixture, so it will depend on Na, Nb, Nc, Nd, where N represents number of moles for A, B, C and D respectively. So we have already arrived at this particular equation which states the Gibbs free energy is equal to mu A Na plus mu B Nb plus mu C Nc plus mu D Nd for the 4 components A, B, C, D. Now let us take the derivative of the left hand side. We know the basic from the fundamental equation that dg is equal to minus s dt plus v dp, plus considering the components, we have to take their derivation of and add mu A dNa plus mu B dNb plus mu C dNc plus mu D dNd. This we have already arrived at in our previous lecture. Now, when we look at the right hand side, since we are taking derivation, so each function has to be derived separately. So dg, from here dg is equal to, first mu A is constant, then dNa, plus now Na is constant, then d mu A. Similarly for other components, plus mu B dNb plus Nb d mu B, plus mu C dNc plus Nc d mu C, plus mu D dNd plus Nd d mu D. Now since these left hand side and right hand side are equal, so we get minus s dt plus v dp equal to these terms Na d mu A, Nb d mu B, Nc d mu C, Nc d mu C and Nd d mu D, and the other terms cancel out. Correct? Okay. Now since we have considered the particular case of the system containing ABCD, but this relation will hold true for any system containing any number of species. So we can generalize the equation. This equation can be generalized in the form of minus s dt plus v dp is equal to sum over j equal to I to omega n j d mu j. As you can see here, Na d mu A plus Na d mu A plus Nb d mu B plus Nc d mu C. So we can just put a general equation here by summing up these values. So this relationship is known as Gibbs Duhem equation. But for a system with constant temperature and pressure, for constant temperature this value will become 0, and for constant pressure this value will become 0. Therefore, finally the Gibbs Duhem equation becomes of the form, the left hand side is becomes 0 for constant pressure and temperature, and the right hand side remains as such. This is the form of Gibbs Duhem equation that we will follow. So this is another representation of how the Gibbs Duhem equation can be arrived at, and how the summation ni d mu I will be equal to 0. So we already know dg is equal to mu1 dn1 plus mu2 dn2 until all the number of components are accounted for, until mu j equal to mu j into dnj, which finally yields dg. At constant temperature and pressure, this value will become 0, and what will remain is sum over ni d mu I equal to 0. You will understand more about it if you go through the notes that I have attached with this class. Now, this expression relates how chemical potential can change for a given composition while the system is at equilibrium. Now, for a binary system, how we can rewrite this equation? We already know n1 d mu1 equal to plus n2 d mu2 equal to 0. So we can rewrite it as so this is how we arrive at the equation as shown here for a binary system consisting of two components. Here they have taken components A and B. In this example I have shown for components 1 and 2. Here they have calculated the d mu for component B, but I have calculated for component 1. So this can be done for a binary system. What are the applications of Gibbs Duhem equation? As we have already seen, it is helpful in calculating what partial molar quantity for a binary mixture by measuring composition of the mixture, which depends on the total molar quantity. Another important application is calculation of partial vapor pressure by calculating the total vapor pressure. Since all these calculations require curve fitting procedure, but using experimental tabulated data, the accuracy of the calculated values can be compared to the accuracy of the original experimental data. These applications will become more clear if you can continue doing this numerical and find the answer for this problem. Please submit the answer before the next class. With this, I conclude today's lecture. If you have any doubts, do not forget to ask. Thank you for your attention.